Hey, so just as a quick heads up, this series is my unfiltered ideas of how I understand certain things about calculus. So by its very nature, it may contain some stuff that may be uncomfortable for viewers under the age of 18. I promise there really isn't nothing too bad, but just so people can feel safe watching my videos. If you are sensitive to certain topics, just viewer discretion is advised. So I had a new idea for a series, right? Let me give some context. So currently I am taking AB Calculus on Khan Academy. I've got into about like 20% through it so far. But I was thinking, so I've still got like 80% of calculus to go through, right? So that means that I'm in a interesting position here. Because you can always learn something, but you can never unlearn something. Once you've learned something and known it for like a very long time, it becomes harder and harder to remember what it's like not to know that thing. And also it becomes harder to remember the misconceptions you may have had before. So because I have a very limited understanding of calculus at the moment, I was thinking it might be interesting for me to just explain what I know, what makes sense, what doesn't make sense, from what I've done so far. So I've basically gone up to limits, and I've started differential calculus. And I've watched some YouTube videos about like what calculus is, right? So I want this to be structured, so I'm not just all over the place, because that's what I tend to do when I don't have a plan. So first, I just want to basically, what do I want to do first? I'm thinking I describe what calculus is to me, because like all of this is my understanding of it. Do not take anything in this video as fact, because I'm literally learning right now. I'm not in a position to be teaching. So yeah, I'll explain what I think calculus is. I'll explain what makes sense to me at the moment, even if it, like, I might be wrong about it, but so far I think like it's something I think that I am correct about. And then I'll explain what doesn't make sense. So that's the plan. Hopefully when I erase, it gets rid of the background. That's so annoying. Well, what can I do? What can I do about that? I guess, I can use the orange paintbrush as the eraser. So problem solving. So first off, what is calculus? Oh, by the way, I changed the background because it's kind of getting bored of the old black background, red marker. I don't know. I also wanted to spice things up a bit. What is calculus? I looked it up on Google, and it basically said calculus is like there's two main things for it. There's differential, I'll just put diff, and integral. Just put. So my understanding is differential. So I have a strategy for distinguishing differential calculus from integral calculus. I suppose I will say it. Actually, I'll make a note to say it by putting this here. Because before I go into that, I want to explain basically what I view calculus as a whole, like on a very broad level. So I watched this YouTube video, and this guy was basically like, calculus is the culmination of everything you've learned in math. And he said like he was disappointed that most people don't take it because it's like, I guess, I wrote something down, like an analogy. I kind of just want to read it. Yeah, for this, since I'm not teaching, I'm just going to be super open about my thought process when it comes to approaching things like this. Just because that's the whole point of the series, is I'm trying to figure stuff out, so I got to be honest with how I understand it, even if it may be a little embarrassing sometimes. Okay, embarrassment is weakness. You can feel embarrassed, but like, that's subconscious. Like, some people just are subconsciously embarrassed, subconscious anxiety, and there's a level that you can't control. However, there's a level that you can control. Because if you consciously say, I do not care what others think about me, at least you should care a little bit, because what others think about you says a lot about who you are. Because if like a lot of people tend to not like you, then there's probably an aspect of you that they don't like. That doesn't mean that aspect is bad. Sometimes that aspect can be something like honesty. A lot of people don't like me because I'm very honest. I try and tell people things with love and not hate. But at the end of the day, honesty is probably what has broken most of my friendships over the years. Don't know why I'm getting so personal. The point of me saying that is just that I have a way of doing stuff. I always am open to feedback, and if I feel like I messed up, I'll apologize. But other than that, I mean, if people don't vibe with my style, hey, I could care less. You always want to be open to like other people's thoughts, because that's how you can't just close off everybody's opinion of you, because that's how you become like obnoxious and not your best self. You want to value it, but you don't want it to be the primary factor of what makes you who you are, I guess. Like, you should always be the person that you want to be at the end of the day. But other people can give you an idea of potential weaknesses you have. Because although a trait can be positive, like honesty, and people can dislike it, most traits that people dislike are negative traits. Like, maybe you don't listen, maybe you talk over people, interrupt them, maybe you only talk about one thing, maybe you're like condescending, like a lot of stuff like that. And you may not realize it until someone else makes you aware of it, which is why you always got to be open to that. So anyways, let me find this analogy. Okay, so here's what I put. So calculus is the final boss in a video game where it uses everything you've learned plus one final trick, and the boss theme is a remix of the songs from the previous bosses that plays in sync with what attacks it's using. When the boss does his final trick, it plays a motivational, epic version of the melancholy song that plays at the start of the game, symbolizing how much you've changed and how confident in yourself you've become since then. So what do I mean by that? So basically, like in video games, like the bosses that come before the main boss usually have like a trick. maybe one boss uses like lightning attacks. Maybe one boss uses fire attacks. One boss uses water attacks. But often in the final boss for these kind of games, it's like a combination of everything. It's like the ultimate test, I guess. So that's what I view calculus as, is like the final boss, the ultimate test of everything you've learned, plus some new stuff, I think. But since it's building off of stuff you've already done, most of the new stuff is just an extension of the old stuff. So, yeah. So, now why is that? Oops. Why is that important? What? Oh, I have the white color. I see. Why is that important? Two reasons. One, it actually made me really excited about doing calculus. There's certain TV series that have a trope where like the main character overcomes all these obstacles and then becomes stronger and stronger. And at the end, he uses everything he's learned to defeat the enemy or whatever. Blah, blah, blah. That hypes me up. And that was like, I guess, that is my general understanding of what calculus is a combination of everything that you've done before on hard mode. So, yeah, that's what I view calculus as. Now to get into differential calculus versus integral, integral calculus. So, I have a paper that I kind of put stuff on explaining how I view each one. So for integral calculus, by the way, I watched a lot of YouTube videos about like just what calculus is on a broad sense. Mainly because, well, I don't have to say that. But yeah, my understanding of integral calculus, I would like to cite the YouTuber I got it from. I'm sure I can find it real quick. It's called This is the Calculus They Won't Teach You. And it is by the YouTuber A Well-Rested Dog. I will link it in the description. But basically, it kind of helped me on a basic level, I guess, understand the difference between differential calculus and integral calculus. Or at least give me an interpretation. I could be completely wrong. That doesn't, just because what I'm saying isn't true doesn't mean the video is wrong. It just means I misinterpreted it. So starting with integral. Integral calculus uses a pizza analogy. So these people are trying to find the area of a circle, right? Early on, geometry was like the only form of math. And triangles, make sense. Width times height, so 1/2 WH, I guess, HW. Square is just, or I guess it would be base times height, is what they say. So 1/2 BH is just half a square. A square is simply just base times height. But a circle is very, very confusing because there's like, it's not a square, it's not a triangle. Does it have one side? Does it have infinite sides? Does it have 0 sides? It's a mystery. So this philosopher dude was like, okay, so to understand something that doesn't make sense, let's connect it to something that we do understand. So what he did is he cut a circle into 8 pizza slices, right? And I'm saying pizza slices because that is something that we can understand. I don't know if they actually had pizza back then. But he said, let me cut a circle into 8 triangle-like shapes, basically. Because they understood triangles. And he was like, what if I rearrange those triangles to make a shape I do understand? So we did 1. Each of these are just 1 slice. So I can number the slices in this sense of 1, 2, 3, 4, 5, 6, 7, 8. So this would be slice 1. This is obviously not to scale. 2. Yeah, like this would be an example of like when I fast forward. I'll make sure not to say anything important when I fast forward, just or I'll try not to say anything important when I think I'm going to be fast forwarding. Because when I do say something important, I obviously want to include it. So better to say it when I have this picture done rather than before the picture. So now, since I just said that, this would be an example of when I go into the future. Second thing. So I was watching that, when I was watching that video by a well-rested dog, this is the calculus they won't teach you. I was like shocked because for my channel update, I was talking about how like they kind of they don't teach you math, they teach you factoring, they teach you limits, they teach you like just the concepts and not how they connect to everything else. So you're essentially just memorizing rules. And there was actually a part of the video where it said there was debate among like mathematicians about how calculus should be taught, because a lot of people like they go into calculus trying to understand and learn things on a conceptual level, but then as more and more stuff is presented that they need to know to pass the exams and stuff, that just becomes impractical. Because obviously understanding, or I guess not obviously, but understanding is difficult. It takes time. And memorization is, for some people, it's easy and it's quick. And when you're just trying to make good grades, which is perfectly fine. I mean, good grades correlate to money because an opportunity. So it's nothing wrong as a student to try to make good grades. If anything, it's good, because even though understanding something may help you understand the concept better fundamentally, if you're not making good grades, that can actually affect your future. And you can't go back and like fix your bad grades, but you always can. After you memorize something and you have free time, you can go back and go over it again to understand it on a deeper level, especially if it's something you need for your profession or whatever. But I mean, that system is obviously dumb because it just is inefficient. You memorize something temporarily, then when you're done with the class, you either move on and memorize what comes next, or you go back over everything basically from the bottom up so you can actually have an understanding, which is kind of like what I think the point of the class should be. But hey, that's just my opinion. But yeah, anyways, they were saying that perhaps the history of how calculus came to be and like the mathematicians that taught it, if that was incorporated into the calculus class itself, it would help people understand the, I guess, roots of calculus and the problems it was trying to solve, I guess. Because if you just teach all the rules of calculus, there's a good chance that the people that are being taught like have no clue how it connects to anything else or what the purpose of it even is, or what it even means. Remember, math is a language. You can memorize what words you have to say for certain things, but if you don't understand what those words mean, you're never going to be able to talk to people in the real world, right? But yeah, basically he was talking about at the end, there's this, I think it was a professor or a former professor, and he was like, yeah, I really don't like how calculus is being taught right now because it encourages the students to memorize over understand. And I was like, wow, that is exactly how I feel currently. And this video was made, and I watched that video after I made the channel update, which I'm kind of glad, because it was since I watched it after, the stuff I said before was like just purely my own, how I perceived the current learning system without any other outside opinion. Like that was a conclusion I drew just completely by myself. And the fact that there's someone else that has that drew that same conclusion. And this was recently. The video was made just a year ago. Because the YouTuber, a well-rested dog, interviewed this guy. For someone, especially someone like a math professor who has such good history in mathematics, to say that like he sees the same problem that I do, I think that means that the potential for change is actually there. It's not like I'm just the only one who thinks like math should be taught differently than how it currently is. And it was interesting to see because there's a petition to basically incorporate the history of calculus into how calculus is taught so the students can actually understand it. But it didn't really, it kind of fell off pretty quickly. And that was in 1990, I think. And we still have this, or at least I still think, math is not being taught the best way it could be. Which means there's potential for change, because it's not like I'm the only one who sees these issues. Other people do too, which means that they probably exist. If a lot of people are seeing the same thing, there's a good thing that thing is actually an issue. So, yeah, back to, that had to do with calculus. So I'm going to keep that in this video. It didn't have to do with what I was talking about beforehand. Beforehand, I was talking about integral calculus and the pizza thing, right? So this philosopher dude, he arranges the pizza slices as so, and says, you know what, that kind of looks like a parallelogram. And a parallelogram is just a rectangle, but fancy. Yeah, so I was tempted to Google what the area of parallelogram is, because I don't want to be spreading false information. I remembered that's not the point of this series, at least if this continues as a series, which I hope it does. I would like to keep doing this as I learn more and more about calculus. Nothing I say in these videos should be taken, or at least like the mathematic information I say could not be used by you. This is coming from someone who is just figuring stuff out. This is not for teaching purposes. Therefore, that means we can figure out the area of a parallelogram using logic. Because if I'm wrong, womp womp. Here we like to problem solve, not just Google. That's just how we roll. So I was like, okay, area of a rectangle is obviously base times height. That's the base would be at the bottom. And the height would be the dotted line. So the triangle things on the side, that would just be, oh, wait a minute. Because they make a square, like each triangle, the area is 1/2 base times height. So like it'd be B for like that triangle specifically, H for that triangle specifically times 1/2. But since there's two of them, we can just do base times height of the triangle, which means we can just multiply the base times the height of the whole parallelogram, and that'll give us the area. So cool. So yeah, I basically said that looks like a parallelogram, and we just proved that parallelogram is just a rectangle. Fancy rectangle, but a rectangle nonetheless. So he said, okay, what if I keep making the slices smaller? So instead of 8 slices here, you would have like 16 slices. Like a lot of slices. And the more and more slices there were, the straighter the parallelogram got. So I said, okay, what if I had infinite slices? So a circle, there's like so many slices you can't even see them. That would make a shape like this, right? And if that shape is made from the infinite slices of the circle, that means that shape is the area of a circle. And there's a little more to it that I don't really remember, but also it's not super important. I don't just want to say everything like I did and copy this video. Okay, so before going back to the subject of the circle thing and how it relates to integral calculus, I know I said I wanted to work on having one train of thought and finishing that train of thought before I switch to another one. However, for things that I really think are important and that like it could be bad if I forget them, because like most things aren't gonna go away if I don't say them instantly. However, this is something that I kind of just realized just now, so I want to make sure, partly so I can, for me, so I know to put stuff in the video saying it, and to address why I guess I have that stuff in the video for people watching. So because this series is basically purely how I understand stuff, with no filters, no nonsense, no lying, that means by its very nature, it may contain some more, I guess, real stuff than my normal videos, and because of that, there's some things that may be more mature that might not be suitable or comfortable for younger viewers to watch. So I will address what like I'm referring to later, because like one strategy I have for something in particular is like a little mature and maybe upsetting to some people. So, but I'll talk about that later. I just wanted to make sure I said that, got that out of the way, so I 100% don't forget, because the last thing I want this channel to be is an unsafe place for people. Anyways, okay, back to the circle. So how does that relate to integral calculus? So my understanding of integral calculus, I'll scroll down. So integral calculus is like, you have like a weird shape, like that, for example, and you shoot it with a laser. That completely incinerates integral the object into just a pile of dust. And instead of drawing out every single dot, I'm just gonna use the fill tool. But this is supposed to represent just like a bunch of infinitely small dots. By the way, infinitely small numbers are referred to as infinitesimals in calculus. But because that word is kind of new for me, I'm probably not going to use it that much. So you convert something that is like a solid shape into basically a fluid state. So that way you can, or like fluid is like liquid or gas, but like by fluid, I mean, if you put this into a cup, it would just get like stuck and it wouldn't fill the shape of the container. Which means if we were trying to measure the volume of this object, just saying, well, how much of the cup does it fill, would not be an accurate representation of its actual volume. Or I guess a better way to picture it would be, let's make the cup bigger, right? Let's say we have like a big measuring cup that has like, that measures like how the volume of an object. So if we put this into our measuring cup, I'll say this is like 10 and this is 1. So when we put this bad boy into our measuring cup, we put that in the cup, it would like go into the cup like this. And even though technically it goes up to like around 9.5 on the scale, that's obviously not the volume of the object, because I'll use a different color to represent this part. There's still lots of area that isn't being filled. And that area is, or the volume of those like blank spots, or the empty spots, is basically being factored into the volume of the main thing. It's like all of this blue stuff right here is being counted as the volume of the shape. So in practice, like when we measure this object, I'll start using white again. It measures from the measuring cup. What it's measured looks like this. Actually, probably a little taller than that. It's like boom, boom, boom. Actually, you know, I'll put it side by side just so we can visualize it. It looks like boom, 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 boom. So this is what, if we use this measuring cup as like an end-all be-all describer of the volume of the shape, this is what it would be saying it was, whereas this would be the actual shape. And obviously this is not, this is incorrect, because it includes the blue stuff that we obviously know is not a part of the actual object. So finding the volume of, using the cup to find the volume of the shape would not normally be accurate. It would give a greater amount than what the shape actually is. So integration, let me see if I can use the bucket tool to get rid of the blue. Looks good enough. Whoops. So what integration does is it breaks by just incinerating the object into just like a ton of tiny dust particles. You can find like the accurate area of the object. Because when we put, okay, so as of now, this recording has been all in one sitting. I have paused it to like use the restroom and stuff, but in like 5 minutes, I'm going to be doing something else. When I come back after those 5 minutes, it will be like a lot of time will have passed. So it won't be like in one sitting, just to let you know. So I'll try and say everything that I want to say in these 5 minutes that I have. So basically integration, I said it like turns it into a vapor, but a vapor is like liquid and gas. So I use the word incinerate because it starts with in. That's the only reason I use that. But like normally the word would be disintegrate or disintegrate, and that starts with di, and di is the start of diff in differential calculus. So I don't want to use the word incinerate just because it's too similar to disintegrate. And the last thing we want from like a play on words or whatever that we use to remember something is it to be confusing and mixed up with the exact opposite of what we're trying to remember. So that's the first thing I wanted to say. I'm not going to use incinerate. So then I was like, okay, what word could I use? So for now, until I come up with a better word, I'm going to use the word vaporize, because I'm like, that's when you shoot something with a laser, you vaporize it. And then I was like, holy cow, That's why vaporize is called vaporize, because it turns something into a vapor. Like in the cartoons, like Dr. Doofenshmirtz shooting a laser at the moon, vaporizing it. It like turns it into a bunch of dust, giving it the properties of the vapor. So that's what vaporizing means. I was like, huh. That's something new I learned. That's why it's called vaporizing. So yeah, integration is vaporizing the object to make it have the properties of a vapor, so we can measure it. So now when we put in the cup, I mean, obviously it like may just like enter like that, but yeah, I'll just fill it in real quick. Oh god. So yeah, when we fill it in, obviously it looked like that, so, or like it might look like that if you just like plop the dust in there. But let's assume that the dust falls on an even level. Gravity pushes it down to where it's just a straight flat line. With that logic, I mean, you could say like you smush it or whatever, blah, blah, blah. That's probably too much. This is all dust, right? I won't fill this in just to kind of like help visualize the point I'm trying to make here. So like all of that is dust. I think if I use like this, it might make it look cool. Yeah, there we go. It's like now, it's like not perfectly filled, but like you can kind of see how it could be considered like dust-like. Yeah. So now when we fill it in the cup, it gives us an exactly accurate measurement of the volume of this object. So like if that's 1, that's 10. In actuality, the object would be like have a volume of like 3. Whereas when before it had like a volume of like 9.5. So yeah, that's basically what integration does, in my understanding. For all I know, this is literally completely wrong. But integration breaks something into infinitely small parts, so it can be measured. So since I don't have much time, I think for now, that's where I'm going to stop, at least until I get back on again. So I'll make sure not to learn anything new before I do the next recording, because there's still more stuff I want to say. I'll just say it after I finish this thing I got to do. Okay, I am back. I think it's been about 2 to 1.5 hours since I got off. So we just finished talking about integration. So I used a solid object being vaporized into dust so it can be measured by a measuring cup as like a analogy, I guess. In a literal sense, my understanding of integration is, well, I don't understand it fully, but I understand parts. So these are all things that I've kind of just picked up on from different YouTube videos. I'll link all the ones that I watched before this regarding calculus in the description. So integration, do I want to talk about this now, or yeah, I'll do it now. Actually, no, I'll do it later. Okay, so now we focus on differentiation. So differentiation, I'll box all this up just to show this is all integration. I'll just do a box around this for now. And I'll put in blue integration. And now for differentiation, which I think I know more about than integration. So differentiation, my understanding is it's getting really close to something, but not approaching it. So differentiation, in my mind, my understanding, it is just limits. Of course, it's not just limits by itself. There's more to it, but if I had to... So the reason I view this as like the definition is because though limits is not the only part of differentiation, from everything I've seen so far, every aspect of differentiation relates to limits in some way, shape, or form. So when I'm trying to remember what it is, if I just say, okay, differentiation equals limits, from there I can like branch off and be like, okay, limits is approaching something, but not ever going exactly to it. And then that relates to instantaneous rate of change, which is another key aspect of differentiation. Instantaneous. I'll just pause while I write this. Okay, so yeah, differentiation finds instantaneous rate of change. So, as an example, if we have a line and we have 2 points on a line, to find the slope, we do change in y over change in x. And to do that, we just do y2 minus y1. Actually, no, it would not be the triangle. Y2 minus y1 over x2 minus x1. I'm not going to write that down. But basically, to do it, we need x1, y1, and this point would be x2, y2. So yeah, you need 2 points to find the change in two things, because if it's just 1 point, how do you find a change? So that's where differentiation comes in. So essentially, there's two forms of differentiation. There's formal. Actually, I'll write them down first, and then I'll say what they are. Okay, so there's two forms: formal form and alternate form. Before I explain the difference between them, at least the best of my possible ability, I'll explain what they're trying to find. So when you use differentiation, it's because you want to find a derivative. I believe a derivative is literally just instantaneous rate of change. Derivative. Or it communicates instantaneous rate of change. But I believe their definitions are... I don't want to do this. I'll circle it. Pretty much interchangeable. It's just instantaneous rate of change takes a while to say, so you just say derivative. And there's two different ways of expressing the derivative of a point. Because when you have differentiation, you're essentially finding the instantaneous rate of change, which means how fast is something going at 1 point. Which it can be used on single lines, or like straight lines that have like a constant slope, but it also can work on curvy lines, which is why, well, I guess that wouldn't be a function. It can work on functions like this. Dang it, I keep... Okay. So any given point, let's say like this is the... Oops. So this is the... axis, right? Or axes. Differentiation could help you find the velocity of this point exactly. So like if this, with this line, if it were to continue like at this point, if it stopped changing direction and just kept going forward, differentiation or the derivative would give you the slope of that line. So it's basically like slope. You're still finding the slope of a straight line, but it's kind of like how with triangles and using sine and cosine for triangles that don't have 90-degree angles. The method to find missing sides and missing angles is a little different. But in reality, it really is just splitting a triangle that isn't, or that doesn't have a 90-degree side into two triangles that do have a 90-degree side, and then solving both those triangles. The formula has been like simplified, so it kind of like does both at once for you. But I think a lot of things in math are just making something that doesn't make sense by making it something we understand already. Because like we understand how to find the slope of straight lines, but we don't understand how to find, or I mean, I'm kind of just talking generally. We don't understand how to find the slope of curved lines because it's constantly changing. So the solution is we turn the curves into straight lines. So yeah, let's say we wanted to find the instantaneous rate of change of this point right here. So there's two ways of doing this. The first, let's say this point is x 1 f of x. Actually, I won't do x1. There's no reason to do that. Now, this is definitely going to be the part of the video where there's probably a lot of inaccurate information. Because I don't want to look at my notes, because I just want to use my understanding. And also, I mean, I need to learn this stuff, because I need to finish this calculus class pretty quick. So this series is also kind of just motivation for me to actually finish calculus, which I do find it interesting, but I also like making videos, so this is kind of like a happy medium. I get to make videos while also learning calculus, and I'm just documenting the journey. So yeah, so we're trying to find the instantaneous rate of change. How do we do that? Well, first, by the way, when I say f of x, that just means the y-axis. It is a little weird that the y-axis and the function itself like are often called f of x. Like this line may be called the function f of x. I don't know why that is. That is something I do not know. So, oh, I get it. Okay, so like because this is x, right? So this is, the y value would just be the function with x plugged in. So it would be that. Because if we just put y, then like we can't, the reason we can't just put xy is because for our second point, we're going to put something different in the parentheses. Or we're going to add something inside the parentheses. So, and what are we going to add? What are we going to add? So what we're going to add is point H. It's just another, yeah, so we just pick another arbitrary point on the graph. And let's say, or actually, I mean, basically what you do is, because we're just picking a random point, we don't know, I mean, you could probably figure it out, but we don't know just by looking at this the exact number of, or the exact amount of distance between these two things, right? So we just say, okay, let's just say that distance is h, and h is equal to the distance between these 2 points. So now that we have like this h distance thing, we can actually label this point in terms of h. So this point would be, first of all, let me get rid of the, we're going to do this. I'll write it and I'll start using different colors. I'll write the h thing in blue. So yeah, the distance between those two things is h. And this point right here, likewise, would be, I guess I'll make the point blue too. Because we know the distance between this point, which is x, right? And this point, which we don't know currently, is h. We can actually write the distance or the x value of this point as x plus h. Again, it's a case of we're using things we understand to find things we don't understand. Like we understand that this point is x, f of x, but we're trying to find the instantaneous rate of change. So we're putting a second point to allow us to communicate that, because, yeah. So if x is x plus h here, then what would f of x be? This is why we don't use y, is because since we used f before, we can just say the y value is the input of x plus h into the function. And now we can use rise over run to find the distance or the tangent line between these 2 points. So y2, did I write it? I didn't write it down. But yeah, we did y2 minus y1. I'll go for this, I'll use white again. Actually, for math, yeah, I'll just use white. Actually, all this white is getting hard to see. I'll use black. So y2 is, I guess I'll label these as x2, or x2, y2. x1, y1. I don't believe what you label as x1 and y1 versus x2 and y2. Like, I think they're interchangeable. Like, this could be x1 and this could be y1 if the other one was x2, y2. But I think that changes the math a little bit. Actually, you know what? I'm not just gonna think it changes the math. Before I've made assumptions, and those assumptions have been incorrect, and that's not good. You always want to check your, or you always want to have a reason for something. So let's see, if we have like 7 minus 2 over 5 minus 5, is that different than, or is that equal to 2 minus 7 over 5 minus 5? Interesting, it is. Or they're both undefined. That looks like a multiplication sign, by the way. Let me just make that clear. So 7 minus 2 is 5. So this becomes 5 on the numerator. 2 minus 7 is negative 5. So this one becomes negative 5 on the numerator. 5 minus 5 is 0. Denominator 0. 5 minus 5 is 0. Denominator 0. So like before, like we subtracted 2 here and subtracted 7 here. So like I guess you can imagine we're technically swapping which values we're subtracting here. Like if I were to have one value in blue So let's say the 7 and the 5 are in blue. Or the 7 and this 5 in particular are in blue. And the other ones are in red. So the 2 and this 5 are in red. And this 2 and this 5 are in red. Even though, like, it's easy to tell the difference between the top and the bottom, but the bottom and the top, because we have 5 twice, it looks the same, but in actuality, we really are switching them. The blue box moves to the right and is subtracted. The red box that's being subtracted moves to the left, and it's no longer being subtracted. So those two are equal. Let's try something else. Let's say, and just in case things aren't super clear, the boxes you can view as like x1, y1, or no. Like y would be on top. Like y2, x2, y2, x2, and the red ones would be x, no, y1, x1, y1, x1. So yeah, I'm trying to prove this. What's that? I'm trying to prove that the order, I'm trying to see if the order matters of what you choose to be y2 and y1. Or if you can just do y1 minus y2 over x1 minus x2, see if that gives the same thing. Okay, experiment number 2. Let's say we have, where's my cursor? There it is. 4, whoops. Actually, just to keep things organized, I'll do it under this right here. Just a dotted line to show we're separated. So we have 4 minus 7 over 3 minus 9. I'll do the experiment and tell y'all if it works or doesn't work. Okay, turns out it works. So what you choose as x1 and y1 and x2 as y2 doesn't matter. The more you know. But anyways, from there, we just use the we do what we did over here. We just plug in our points. And we have our points labeled here. So we have y2 minus y1, let's say. So f of x. Actually, nah, the order shouldn't matter. It doesn't matter. We just proved it. y2 minus y1, which is f of x. Over x2, which is x plus h. Minus x1, which is x. So we can get rid of these parentheses to just get x plus h. So like this would simplify, or just the denominator at least, to x plus h minus x. And because we have one x, if we have x and a minus x, that means together they make 0x. So it just leaves h. So our final fraction would look like f of x plus h minus f of x over h. Sorry, I left for a second. What was I? Oh yeah, so we just found the distance between these 2 points. So we could essentially just or not the distance, the slope, because remember, slope is rise over run. So we found the slope of this line right here. But as you can see, this line isn't really the direction this dot seems to be going. If it were to continue in either direction, the line would probably look, it would look more like that, except without the random zigzag. So then, shoot, what's the point of this useless information right here? Well, here's the thing. Now, we can say, okay, well, what if h was really, really close to x? And that's where the limit part comes in. Let me just separate the work with like a boo. So let's say h got really close to x. Or actually, I guess that's not technically true. Let's say the distance between x and x plus h got shorter and shorter. How do we do that? By making h approach 0. So the limit of as h approaches 0. You know what, I'm gonna erase the stuff on the left here because we figured out that it worked. So I don't really need it anymore. And I do need space. Bye-bye. Do I leave you? No. And now we can get rid of this line. So as we write this, this is the part where the differentiation comes in. So what you can't just write the limit as h approaches 0 is equal to this, because we have to define what f of x even is in the first place. So like you'd think you'd write f of x. Wait, does it start with a limit or does it start with? Oh, I think the f of x comes after actually. So it'd be like the limit as h approaches 0 of f of x but because we kind of technically made like another point called h, or not point h, but we made a point that was h distance away from x, but there isn't actually like that on the graph. We have to put this little guy here. And I have a way of remembering like when to use integration and differentiation based off this little guy right here. But I'll tell that analogy later. Actually, I think I'm going to take a break. Just chill. Okay, this last part of the video, I kind of need to speedrun. So what we just did was formal form. And that's for differential calculus. So the other way of doing differential calculus is alternate form. So I have a graph right here, right? Usually we would pick a point and we would call that point h. Or at least that's what we do for formal form. And then we'd find the distance like traveled y-wise and the distance traveled, I guess it would look visually Yeah, I'll draw a triangle. Like the distance traveled x, and the distance traveled f of x. But we know f of x because it's just f of x plus h. So for alternate form, instead of using h, we just kind of use, or at least I believe, we use the origin. So the origin we label as x f of x. So our h is the origin, and our point we label as a f of a. So to find our instantaneous rate of change, because obviously the dot isn't going like the line I'm drawing right now, we bring x f of x as close as possible to a f of a as we can. So how would we write that? We'd write that as the limit as x approaches a of f of x prime, that's what the sign means, is equal to rise over run. We can label this y, or that would be x. I'll pause right here while I label them. Okay, so our x1, y1 is our a f of a, and our x2, y2 is our x f of x. So y2 minus y1 would just be y2 is f of x minus y1, which is f of a, over x2, which is x, minus x1, which is a. And this would be the alternate form right here. That's right, alt. Actually, I'll just pause again. Keep things as quick as possible. Okay, so we have our formal form that looks like this. We have our alternate form that looks like this. I believe you can use either or, but for questions that like you may receive on a test, I think you need to know both forms. So that leads to the question, what does this thing mean? So I explained it before, but it's a big part of differential calculus. So this is diff calculus. You go from f of x to f prime of x. And I believe integral calculus is like the inverse of differential calculus. So integral calculus is you're given f prime of x, and you have to go to f of x. So the reason why there's a mature warning at the start of the video is my strategy for remembering this is called the divorce strategy. Let me get the paper. Okay, yeah, just to make sure we're on the same page. I'm not trying to make fun of divorce or anything. I know it's a serious thing. However, it just happens to help me remember what to use when going from f of x to f prime, and what to use when going from f prime to f of x. So let's say f and x, they really love each other, right? They're in love. And what do people in love like to do? They like to be together. So if they start together, but then are broken apart, and I view this little prime symbol as like a division between them. Because like in marriage, two become one, right? This f prime basically separates them. So differential calculus divorces f and x, or divides f of x. Those both start with di. And into integral calculus, when they start separated apart, because, they're not in love or they're not married yet, integral calculus brings them together by breaking the bond, breaking the wall between them. Or in other words, it integrates them together. And that is the entirety of the divorce strategy. Pretty simple. Now, I know how to do differential calculus, which is just going from f of x to f prime. I currently don't think I know how to go from f prime to f of x. So other than that, the only other things that I really know about calculus are derivatives are often represented as d over d of x. And in, what's the word for integral? I saw someone say it. I don't know. So this is for derivatives. And this fancy thing is for integral stuff. I think, like, derivative is for differential, but I don't know what the term is for integral. But that's integ. Oh, and last thing. dr, or not dr, fancy dr, represents a starting distance between two things that you can, like, adjust. So, like, differential calculus is when something gets infinitely close to something else, right? So dr you can set to, like, I don't know, like 0.1 to have, I guess, a starting, like, set separation, and then as dr decreases and gets closer to 0, it whatever you're doing becomes more accurate. And that was something I learned from, let me check what the video is called. Okay, yeah, that video was called The Essence of Calculus by 3 Blue 1 Brown. Incredible video. It's the first part of a video series called The Essence of Calculus. If the first video is anything to go off of, it seems like a very, very high quality and well-made series, and it really helped me understand kind of integral calculus, or what it was trying to do, with this really cool circle and, like, ring strategy, which I will not go over. You can watch the video if you want to see more about it. But dr related to that. So yeah, that so far I think is everything I know about calculus. So yeah, this is episode 1. Episode 2, I don't know how much I'll learn. Maybe a lot of this I'll realize is wrong, but we shall see. We shall see.